Hello, BC students. Thank you for coming back and welcome to our second video lecture, 10.2b. I guess it's our third now that I think about it. Anyway, we're going to go over Taylor's formula and constructing power series for sine of x, cosine of x, and e to the x. Now this is material that you need to know for the AP exam, and it is material that we've covered in class, but I'm going over it for the sake of completion. Assuming you watched video lecture 10.2a about building a polynomial to represent the natural log of 1 plus x, I hope you followed the basic goal of the approach. Our desire is to find a polynomial, basically an infinite polynomial or a power series, a0 plus a1x plus a2x squared plus dot 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 plus akx to the k plus dot dot dot, that behaves like some differentiable function f of x. And the way we approach this is kind of an extension of finding a linearization. We want to find a polynomial that matches f of x in that they both have the same value at 0. They both have the same first derivative at 0, the same second derivative at 0, and the same third derivative at 0, and so on. So I want to start by claiming that if we let p of x be the following polynomial, that is, p of x is a0 plus a1x plus a2x squared plus dot 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 plus akx squared x to the k plus dot dot dot. What I want to claim is that the kth derivative of p at 0 is ak times k factorial. And this should make perfect sense, because as you take successive derivatives of p, each of the constants drops off and all of the degrees get dropped by 1. So as I take derivatives of ak x to the k, the first time I do it, I get k ak x to the k minus 1. The second time I do it, I get k times k minus 1 times ak x to the k minus 2, and eventually I'll wind up with k factorial times ak. Now all the previous terms have gone to 0 because we took derivatives of constants, and all following terms will have at least an x in them. So the polynomial at this point looks like this. There's a constant leading term, and then every other term has an x in it. So when I look at the derivative, the kth derivative of p at 0, all the other terms drop out, and I get a sub k times k factorial. Well, we want this to match the kth derivative of the function f, the one that we're approximating, at 0, and so that means that the kth coefficient in our polynomial that approximates the function f will be the kth derivative of f at 0 over k factorial, and that lets us build a Maclaurin series for a particular function f, provided it is infinitely differentiable. We can use our formula to substitute in for all the a0, a1, a2 values. And that last line is pretty important and worth memorizing, because that's the formula that gives you the Maclaurin series for a function f, which is the same as saying a Taylor series for f centered at 0. And it is certainly the two sides are equal in the interval of convergence, and more about that as we go forward. In summary, this lets us build a Taylor series generated by a function f at x equals 0, as long as we know it's the value of the original function at 0, the first derivative at 0, the second derivative at 0, and so on. Let's use this to go ahead and figure out what a Taylor series would be for the function sine of x. Here I have listed the value of sine 0, and of course the first derivative cosine 0, the second derivative negative sine 0, and the third derivative, negative cos 0. And they come out 0, 1, 0, negative 1. And as we know, what happens as we go forward is that that four-step pattern repeats and repeats and repeats. And that lets us build a formula for the Maclaurin series for sine of x. Here I went ahead and substituted into the general Maclaurin series the values we'd figured out for f of 0, f prime of 0, f double prime of 0, f triple prime of 0, and we wind up with the first few terms, x minus x cubed over 3 factorial, and it continues in the same pattern. 0, 1, 0, negative 1, 0, 1, 0, negative 1. So as a result, you only have the odd exponent terms. And in general, the kth term is going to be something like x to the 2k minus 1 over 2k minus 1 factorial. And now let's figure out how to handle the alternating plus and minus. Well, you want negative 1 to a power. When k is 1, you want it to be positive, so that's going to be k minus 1. And in sigma notation, that would be sum k equals 1 to infinity of negative 1 to the k minus 1 x to the 2k minus 1 over 2k minus 1 factorial. So that's the Taylor series for sine of x, and it is definitely worth mentioning. The signs alternate. X is always to an odd power, x cubed, x to the 5th, x to the 7th, and the denominator is always the factorial of the exponent, and you need to know that for the AP exam. Let me write that one more time. Getting a formula for cosine of x, we could just start from scratch and figure out the first, second, third, fourth derivatives and use the Taylor formula. Or more easily, we can just differentiate the formula for sine of x. So you see the pattern sort of continues. This time it's the even powers of x, starting with x to the 0 or 1 over the exponent factorial, and note that 0 factorial is 1. And so we have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. And this is another very important formula to know. The last one we'll take a look at quickly is e to the x. Now, because of the important property that the derivative of e to the x is e to the x, every derivative of e to the x is e to the x. So any derivative of the function f at 0 will be e to the 0 or 1. And so plugging into our formula for Taylor series, we get the following. So the formula for e to the x is very simple. It's kind of like if we took all the terms of both sine and cosine and made all the coefficients positive and added the two together. Then we'd have the odd terms and the even terms, and it would simplify to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial dot 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 plus x to the k over k factorial plus dot 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 forever. And that would be a Taylor series for e to the x centered at 0, also known as a Maclaurin series for e to the x. I told my sister I was writing these video tutorials for you, and she said I should put fun things in for you. Maybe some funny pictures of cats or something like that. Well, maybe we'll do that in the future, but for today, a joke. I was outside waiting for the sun to rise when suddenly it dawned on me. Anyway, have a great time. Find things to do that are fun. I know these are trying times. I miss you all. I wish I could see you. I wish I could be in class with you. I hope hearing my voice and seeing these stupid little videos helps a little bit. And thanks for watching.